Good morning, friends. Today we'll see few questions or few theorems proved by using mathematical induction principle. Here is the first question. Prove that n cube plus 2n is divisible by 3 for all n greater than equal to 1. So mathematical induction proof consists of three main steps: induction basis, induction hypothesis, and induction step. So first, here is the first step, step 1. Basis. In this we prove that this theorem is true for a smallest number or base case. Here the smallest n is 1. So let's prove that the statement S of statement is true for n equal to 1. So for n equal to 1, n cube plus 2n is equal to 1 cube plus 2 into 1. So 1 plus 2 is equal to 3. So this 3 is divisible by 3. Therefore the theorem is true for n equal to 1. True for n equal to 1. Let's see the second step. Step 2. This is hypothesis. Here we assume that the theorem is true for some k. So therefore k cube plus 2k is divisible by 3. So this is hypothesis. The theorem is true for some k. The next step is induction step, step 3. Induction step. Here we prove that the theorem is true for k plus 1. Prove for k plus 1. So that is k plus 1 whole cube plus 2 into k plus 1 is divisible by, that we have to prove. So let's do it. So k plus 1 whole cube plus 2 into k plus 1 is equal to, here we'll expand this bracket, so by using the formula a plus b whole cube, so k cube plus 1 cube plus 3k square into 1 plus 3k into 1 square, that is the expansion of this bracket, plus this term, that is 2k plus 2, right? So now from this I'll collect the sum, I'll write some terms together. I'll write this and this together. So this will be k cube plus 2k, right? And then remaining terms, this and this, right? So 1 plus 2 is 3, 3k square and 3k. So 3k square plus 3k plus 3. These are the remaining terms. We wrote them together. So now if I take this 3 out from here, this 3 is common in every term, so I'll take that 3 out. So k cube plus 2k plus 3 into k square plus 3 k square plus k, 3 is out now, plus 1 here because this 3 is out. So now if we see, this term is divisible by 3 from hypothesis. In hypothesis we assume k cube plus 2k is divisible by 3, and now this term is also divisible by 3 because 3 is one of the factor of this term. So this is also divisible by 3. So the complete term is divisible by 3. Therefore the theorem is true for k plus 1, and hence the theorem. So this is the proof: induction basis, induction hypothesis, and induction step. So let's see few more problems, few more theorems proved by using mathematical induction. Here is the second question. Prove that n square plus n is even for all n greater than equal to 1. Even even numbers are always divisible by 2. That means we have to prove that this expression is divisible by 2 always. So again, 3 steps. Step 1, basis. In basis, we'll prove this, that this expression is divisible by 2 or is even for n equal to 1. So for n equal to 1, n square plus n is equal to 1 square plus 1, that is 2, and this 2 is divisible by 2 or 2 is even. That's why the theorem is true for the base case. So step 2 is the hypothesis step. In this, we assume that this theorem is true for some k. So therefore, k square plus k is even, right? So next, in the induction step, we prove that the theorem is true for k plus 1. So let's write the hypothesis step, induction step. Step 3 is induction step, where we prove that the theorem is true for k plus 1. Prove that true for k plus 1. That means we have to prove that k plus 1 whole square, we are substituting k plus 1 in place of n or k here. So k plus 1 whole square into k plus k plus 1 is even. That we have to prove. So let's do it. So k plus 1 whole square plus k plus 1, if I expand this by using a plus b whole square, so k square plus 2k plus 1 plus k plus 1, right? So this is the expansion of this term, and this term is added here. So now I'll write k square plus this k, right, as one term or together, and the remaining term 2k plus this 1 plus this 1 is 2. 1 plus 1 is 2. So plus 2k plus 2, so which is equal to k square plus k plus 2 into k plus 1. Now this term from hypothesis is even. In induction hypothesis, we assume that this term is even. If we see here, right, so we have assumed this k square plus k is even. So one term, I'm sorry, so if this term is even and this term is also even, because 2 is one of the factor of this term, that means this term is divisible by 2, that's why this term is also even. So this is addition of evens. So addition of evens is even, that's why the complete term, this term is even. So therefore this theorem is true for k plus 1. Thus proved that n square plus n is always even by using mathematical induction. So let's see one more example. Prove that 1 plus 3 plus 5 plus 2n minus 1 is equal to n square. In fact, this is a well established theorem called as sum of first n odd numbers is n square. Sum of first n odd numbers is n square. So let's prove this by using mathematical induction. Step 1 again, induction basis. Here we prove the theorem for the smallest number or the base case, that is n equal to 1. So for 1, LHS will be equal to 1, RHS will be equal to 1 square, that is 1. Therefore LHS equal to RHS, hence the base case is true, or the theorem is true for base case. Step 2 is hypothesis. Here we prove, here we assume that the theorem is true for some k. So therefore 1 plus 3 plus 5 plus 2k minus 1 is equal to k square, right? In place of n, substitute k, because we are assuming this theorem is true for some number k. So the third step now is the induction step. In this we will prove that the theorem is true for k plus 1. So step 3 is induction. Prove for k plus 1, right? So therefore what we have to prove is 1 plus 3 plus 5 plus 2k 2k minus 1, that is up to kth term, kth term. Now we have to prove for k plus 1. So in place of k substitute k plus 1. So that is 2 into here 2 into k plus 1 I'll write. So 2 into k plus 1 2 into k plus 1. So in place of k substitute k plus 1 minus this 1. So that is equal to k plus 1 whole square, that we have to prove. This is 2 into k plus 1, right? So let's do this. Let's write the LHS. So LHS is equal to 1 plus 3 plus 5 plus 2k minus 1 plus, if we expand this we'll have 2k plus 2 minus 1, that is 2k plus 1. So 2k plus 1. So let me expand this bracket also. It is nothing but k square plus 2k plus 1. So this LHS is equal to k square plus 2k plus 1, that we have to prove. So we wrote the LHS here. So if we solve this further, now from hypothesis we know that this term is equal to k square. So we'll substitute k square for this. So we have k square plus 2k plus 1, this 2k plus 1. Now if we look at this k square plus 2k plus 1, that is nothing but RHS. That's what we wanted to prove. Therefore the theorem is true for k plus 1 as well. So therefore the theorem 1 plus 3 plus 5 up to 2n minus 1 is equal to n square is true. So these were few examples by using mathematical induction, where the process of mathematical induction mainly consists of 3 steps: induction basis, induction hypothesis, and induction step. So keep on watching for more videos on maths and other topics. Thank you.